In this video, we are going to look into spin coupling or signal splitting in proton NMR spectra. In the previous video, we have seen that in a proton NMR spectrum of ethanol, signals due to methyl CH3 and methylene CH2 groups were split into further smaller signals. So those signals, we say, exhibited multiplicity. And multiplicity was due to spin coupling. Spin coupling is the result of the interaction of the applied magnetic field with the neighboring protons. And the number of lines in a signal, or multiplicity of the signal, corresponds to the number of protons on the neighboring atoms. Each neighboring proton can be either parallel or can have spin that is either parallel or antiparallel to the applied magnetic field. If it's parallel, then it reinforces applied magnetic field. If it's antiparallel, then it opposes applied magnetic field. Either way, it modifies the strength of the applied magnetic field. And relative intensities of the peaks, those small peaks that signal is split into, are a statistical ratio of possible spin orientations of the neighboring protons. So if we consider protons of methyl and methylene groups, these are possible spin orientations. In methyl group, there are 3 protons, and so there is one orientation where all 3 spins are parallel to the external magnetic field. There is only one such possible situation statistically. Now, it is also possible that 2 of them are parallel and one antiparallel to the applied magnetic field. There are 3 such possibilities because any of the 3 protons could be the one that has spin antiparallel to the applied magnetic field. So this situation is 3 times as likely as the first one where all 3 are parallel to the applied magnetic field. Next, we could have a situation where 2 of the spins are antiparallel to the applied magnetic field and one is parallel. And any one of the 3 protons could be one that is parallel. So again, there are 3 such possibilities. And finally, all 3 could be antiparallel to the applied magnetic field. Again, only one such possibility. So statistical ratio of these spin orientations is 1 to 3 to 3 to 1. In case of methyl group, CH2, situation is a little bit simpler because we are dealing with only 2 protons. So both spins could be parallel to the applied magnetic field. There is one such possibility. Then one could be parallel, one could be antiparallel. Well, there are 2 such possibilities because either of the 2 protons could be parallel or antiparallel. And finally, both could be antiparallel. Again, only one such possibility. So there are 3 possible states and their probabilities are 1 to 2 to 1. Now let's consider what is a signal due to ethyl group going to look like in proton NMR spectrum. So we are going to consider some general compounds with formula CH3CH2X, where X is either a substituent that has no protons, so that ethyl group is isolated, or is a substituent like OH group in ethanol, where hydrogen is attached to oxygen and is hydrogen bonded. Hydrogen bonded hydrogens do not split signals because of the rapid exchange due to hydrogen bonding. They exhibit only average state, so they do not split signals. So either way, we are observing only isolated ethyl group. If that's the case, then signal due to CH2 group of the ethyl group is split by 3 protons of the neighboring methyl group, and signal due to methyl group is split by neighboring 2 protons of the neighboring methylene group. So that's shown here. So let's look at CH2 signal first. So CH2 signal is next to 3 protons. And we have just seen that these are possible spin states of those 3 protons. So in those spin states, these protons are either going to reinforce or oppose external magnetic field. So they will de-shield CH2 group or shield CH2 group from the external magnetic field. And these spin states have probability of occurring of 1 to 3 to 3 to 1, as we have just seen in the previous analysis. So signal due to CH2 group is going to be split into 4 small peaks. It's going to exhibit multiplicity that is called quartet. And those signals will have intensities of 1 to 3 to 3 to 1. Their separation between individual peaks is constant regardless of the instrument we use, regardless of the strength of the magnet. And it's called coupling constant. That's because it is a phenomenon that is called coupling, and constant because it's constant, it does not depend on the instrument that we are using. When we consider signal due to methyl group CH3, it's going to be split by the neighboring 2 protons, CH2 group. And CH2 group can have these 3 possible spin states in the ratio of 1 to 2 to 1, as we have just seen. So signal due to methyl group, CH3 group, is going to be split into triplet. And intensities of the individual signals in a triplet will be 1 to 2 to 1. So you can see that splitting pattern is n plus 1. So multiplicity of the splitting is n plus 1, where n is the number of protons on the neighboring carbons. In this table, we have multiplicity and relative intensities of signals depending on type of splitting. So one neighboring proton is going to split signal into doublet, and doublet has 2 signals with intensities of 1 to 1. We have just seen that triplet has 3 signals, of course that's what triplet stands for, and intensities are 1 to 2 to 1. Quartet, 4 signals with intensities 1 to 3 to 3 to 1. Quintet, that's splitting by 4 neighboring hydrogens, will of course have 5 signals, and intensity will be 1 to 4 to 6 to 4 to 1. Intensities of the signals and splitting number of signals could be predicted by application of Pascal's triangle. So we consider number of neighboring protons, and multiplicity is of course n plus 1, and relative ratio of intensities will be given by Pascal's triangle. So if there are no neighboring protons, then multiplicity is singlet. That means there is just one signal, there is no splitting. And so that means that intensity is of course 1. If there is one neighboring proton, then multiplicity is n plus 1, where of course n is number of neighboring protons, and relative ratio of intensities is obtained by generating Pascal's triangle. So we look at the first row where intensities for the singlets were given. So 1 plus number to the left of 1. There is no number, that's 0. So 1 plus 0 is 1, and we write that 1 in between the 2 numbers in the row below. And same, 1 plus number to the right, that's 0. 1 plus 0 is 1. So we write that 1 in between the 2 in the row below. And so we have doublet that has ratios of 1 to 1. Next, with 2 neighboring protons, multiplicity will be triplets, 2 plus 1. And relative ratio of intensities would be, now we look in the second row. So 1 plus number to the left, 0, that's 1. And then in a third row, we write 1 between the 2 numbers. Then 1 plus number to the right is 1, that's 2. And then we write 2 between the 2 numbers in row below, in a third row. And finally, 1 plus 0 is 1. That gives us ratios of 1 to 2 to 1. And then following this process, we end up with 3 neighboring protons, there is quartet, and ratios are 1 to 3 to 3 to 1. 4 neighboring signals, so again we follow the same procedure. Now if you look at intensities for quartet, it will be 1 plus 0 is 1, and then 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, 1 plus 0, 1, and we end up with ratios of intensities for quintet. And here is for sextet. By the time we get to sextet, we may be able to see these intensities reasonably well, but particularly those end peaks may be difficult to see. Also, sometimes signals are overlapping. So sometimes we may not want to actually try to guess what is the multiplicity and relative ratio of intensities, and we simply refer to signal as a multiplet. So if signal appears to be complex and we are not sure how to designate it, we will simply call it a multiplex. Magnetically equivalent protons do not cause signal splitting. Magnetically equivalent protons are those that have same chemical environment, and of course they have same chemical shifts. So if protons have same chemical shifts, they do not split each other, and we see only a singlet. Here is an example of molecule of ethane. We have two CH3 groups next to each other. But we are not going to see quartet because they have same chemical shift, they don't split each other, and so multiplicity is singlet. Here is another example. We have molecule of ethylene glycol. So CH2 groups do not split each other because they are magnetically equivalent. They have same chemical shift, and so there is no splitting. And of course, as already mentioned, OH group does not cause splitting. OH group in general pretty much never causes splitting because it is hydrogen bonded and there is rapid exchange of protons. So as protons exchange on the OH group, one proton may have spin that is parallel, one that is antiparallel to external magnetic field, and only average state, which is 0, is observed. So there is no splitting. Splitting due to OH group could be observed, but it requires special technique and special conditions, and we will not be covering that in this course. So you should always assume that OH group does not cause splitting. And in this case, of course, two CH2 groups are identical, so no splitting. So be aware of it, because sometimes spectrum appears simpler than you would expect because there is no splitting due to magnetically equivalent nuclei. Sometimes a signal due to a particular proton or group of magnetically equivalent protons will take rather complex appearance, much more complex than you would expect based on simple analysis of signal splitting we have done so far. That will be the case if protons on the neighboring atoms are non-equivalent. So if proton that gives rise to a signal is next to more than one group of protons, to non-equivalent protons, then splitting becomes more complex and takes form of what we call multiple of multiplex. That means that each type of proton, neighboring proton, splits signal individually. And we will examine that on example of styrene. So this molecule right here is styrene. We will ignore aromatic ring. Aromatic protons are between 7.2 and 7.3. We are only interested in alkene protons. So let's consider 3 alkene protons, and they give rise to 3 signals. We would expect for each proton, based on simplified analysis, because it's next to 2 other, or actually 2 protons that are part of CH2 group, we would expect to give 1 signal and be split by the neighboring proton into a doublet. And that neighboring proton, CH, to be split into a triplet by CH2 group. But actually splitting is much more complex, and observed signals are far more complex. So what happens is that each individual proton, because they are different, splits signal separately. So when we consider proton at 6.63, that's the lone CH proton. It's being split by the 2 protons, 2 neighboring protons separately. That's because the 2 neighboring protons are non-equivalent. They are different. It's not ordinary CH2 group where 2 protons would be identical. Here they are different because one proton with chemical shift of 518, is trans to the benzene ring, while proton with chemical shift of 5.56 is cis to benzene ring. So they are different and they split signal separately. And for that, we draw a splitting diagram or splitting tree shown here underneath. So we start with a singlet. Just we draw a single line as a singlet. That's signal due to 663 proton, as if there was no splitting. Then splitting by a proton due to a larger coupling constant. That's trans proton. Protons trans through it. Proton at 5.61 splits signal of 6.63 proton with coupling constant of 18 Hz. And of course, since this is only one proton, it will split signal into a doublet. Separation between the 2 lines of a doublet will be 18 Hz. And so now we draw that splitting tree. We draw it as a doublet. Now each of those signals will be further split into a doublet by cis proton at 5.18 with a smaller coupling constant of 11. And so at the end we observe 4 signals. We call those 4 signals doublet of doublets, because first proton split the original signal into doublet, and second proton split it again into doublet, each doublet into another doublet. So this is doublet of doublets. And note how coupling constants are shown. Here we can see coupling constant of 18 Hz in the final doublet of doublets, and where is coupling constant of 11 Hz. We can see that this is doublet of doublets and not a quartet. It may look like a quartet, but it is not. The reason why it is not a quartet is twofold. You can say it's not a quartet, and for 2 reasons. First, the ratio of intensities of individual peaks is not 1 to 3, 3 to 1, which would be in the quartet. Here it's something else and depends on the individual situation. Also, distance between individual peaks of this doublet of doublets is not that of quartet. In quartet, all the 3 distances are the same, and they equal the coupling constant. But here we have 2 different coupling constants, which will result in different separation, different distance of the signals. So that's how you know it's doublet of doublets and not a quartet. Now, the magnitude of separation, where the signals are, and their relative heights depend on how different these 2 protons that cause the splitting into doublet of doublets are. The more different they are, the further separated 2 doublets are, and this less and less resembles quartet. The more similar they are, signals will get closer and closer. Particularly, the inner 2 signals will get closer and closer to each other, and eventually, if the 2 protons become identical, then those middle 2 signals begin to overlap, or they end up overlapping, and we end up with simple ordinary triplet. Here is another example of doublet of doublets. So a hydrogen signal that is split by 2 different neighboring protons. And you can see this doublet of doublets does not resemble quartet in any way. And in fact, that's frequently the case. In the previous example of styrene, the doublet of doublets did somewhat resemble a quartet, but frequently it doesn't, and it's not that easy to mistake it for a quartet. In fact, it's very seldom that it would resemble a quartet. So when there are 2 neighboring protons, they will either split a signal into doublet of doublets if they're non-equivalent, or if they're equivalent, they will split a signal into triplet. And here is another example, that of divinyl ether, much simpler example because each half is identical, so there are only 3 protons, 3 signals, and each of them is split into doublet of doublets. Keep in mind that CH2 protons also in this case split each other because they are not equivalent. Only equivalent protons do not split each other. In summary, this is the information we can obtain from a proton NMR spectrum. Number of signals in the spectrum tells us the number of different hydrogen nuclei in the molecule. Chemical shift tells us detail of chemical environment of each proton, each type of protons. Area of the peak gives us the relative number of particular type of protons. And finally, splitting of the signals tells us how many neighboring protons there are. This completes our study of proton NMR spectroscopy, and next we are going to look into carbon-13 NMR spectroscopy.